this is the third in the Diffusion set of discussions, and this one is the sort of rather rudimentary, actually sort of, making the sausage kind of discussion, rather than the sort of delectable discussion on sous vide sort of methods. So for that, a lot of it I'm just going to go through sort of little things to be aware of, things to think about for file, and throwing a little bit of discussion on things that Tom has touched upon in the prior. So with that, I thought a good place to start would be some considerations for what you're collecting. So we'll be going over the data collection. We'll touch upon sort of actually doing the top-up, actually doing the eddy, doing the TBSS, which is really comically straightforward, then the bedpost and prop tracks, and I'll touch on DSI Studio. So some of these things, like things to consider when deciding upon your pulse sequence, might not be things that you'll be doing too much of. And similarly, the top-up and eddy, there are some automated scripts at the center which make it a whole lot easier than doing those things yourself, specifically with a top-up. So I'll touch upon what goes into that, but I won't sort of drag you through too many of the gruesome details. So, but things to think about. When you're collecting your diffusion, you're mapping out basically, directional tensors, or however they get represented in the algorithm of your choice. And so isotropic data collection is important. So, if you're trying to work out a path of a vector, if your collection area is not evenly distributed, isotropic, then it's going to make it harder to map that appropriately. As your resolution goes up, your signal to noise for that given measurement goes down, but you get better tracking accuracy. So the actual size of the white matter, the nerve bundles, is way too small to actually work with, and as Tom was discussing, you're really looking at the aggregate shift possible. You're not really looking at the specific fiber bundle itself, just the aggregate movement, the diffusion of water. So, and he also discussed a little bit how as you modify that B value, you can get a more precise measure of the amount of diffusion. As the B gets larger, the delay gets larger, you can actually see things move across the gradient more effectively than when you have a B of 0 and you're just getting the image at the time, essentially. So that's similar to what you get with the higher resolution, is you start to increase your accuracy as you map out those fibers, but you also lose your signal to noise. And the way you experience it in the scanner is it also gets more shaky. So you get it, you do a B value of 1000, and it's not too bad to be in there. You get 2000, 3000, it starts to shake and it's pretty darn loud. As you get higher and higher, it gets more and more shaky and fuzzier image, and it's actually sort of, you get more chance of nerve stimulation. Yeah?
Wait, you mean like physically shaky?
Yeah.
When you're collecting the data?
Yeah.
Okay.
Yeah, it's kind of interesting to be in there when you bump up the B values and it's starting to rock. So as far as if you wanted to make your own shells, which every once in a while you do, you never know, you want to sort of see what you can come up with, this is actually a quite nice I'm really using it here to show what sampling algorithms can look like, but you can actually create your own. So this is when you think about the shells, you can think about your b value and your extended vector that you can pull across. So how precise it gets increases as your b value gets larger. These are multiple shells, multiple b values, so that you can really map out that diffusion. And oftentimes you build more diffusion. You sample the diffusion higher at the higher levels. So, for example, this is if you sampled at 1,000, 2,000, 3,000 equally. The these ones, this isn't necessarily the shell set that you'd want to go with, because you get more directional information out of that higher level shell. That specifically this shell you get more directionality information out of because you have a longer diffusion gradient. So a a shell like this, where you've got the higher proportion on your outer shells rather than your inner shells, is maybe a better makeup of um, your B files, your BVEX. So one thing that will come up repeatedly today is BVALs and BVEX. Um, the BVEX is the tensor direction of this, and I'm using tensor in the vector sort of term, so the multidimensional vector. That is going to this will create sort of a good selection across those gradients, and the B-vals is at what shell level those are collected at, and also you've got your zero B-vals, where you can basically the B-val of 0, you can ignore any concern about your tensor direction or your gradients because you don't give it enough time to ever collect along that. So you have zeroed out those, and you're better off again collecting more at this outer shell. It's going to be noisier, but it's going to be more directional. I'm sure that's a word. So those are two things to think about: your resolution and how you're setting out your tensors, your vector file. Another thing to consider is your phase encoding. Now, both me and Tom and maybe some other people whose lectures I haven't listened in on admittedly have talked about top-up and top-up correction. And a lot of the examples are in the anterior-posterior / posterior-anterior data collection. And you'll sort of remember ones where people's frontal lobes shoot out and they suck in. That's sort of the visual on that anterior-posterior. And that's because as you path through that case space, you're giving it more time to get susceptibility artifact in one direction. So that can cause sort of difficulty in these regions. So you can do right to left as well, but right to left will cause sort of distortion, so that one side, the front, the brain is shifting over to one direction, the other side is shifting over to the other, and that can lead to sort of finding asymmetries in your data, which is weird, but it can be corrected and you get less signal distortion. So while the anterior-posterior is the examples you see most, right-left isn't a bad consideration to do, and things like the HCP protocol are using right-to-left. Another thing to think about is, and this is something Tom touched upon last week, is monopolar and bipolar gradients. That is when you collect it, then you flip it, then you collect it again, and it helps do an internal control for your eddy currents. It's sort of like a good in-scanner way of making sure that you don't get too much effect of your eddy currents. But the new FSL 6 is actually getting better at collecting that. correcting those eddy currents. So I talk a lot today about the newer eddy, which compared to the older eddy, the new eddy is just really great. I mean, not to, you know, cast shade on old eddy, but it's all about new eddy. So the monopolar gradient you can now start using, and that one, it means that you can reduce your TE, you can get faster data collection, and you can still get some correction for those eddy currents in your um, through software correction instead of the hardware correction. So there's some thoughts about when you're collecting your data, just to give a little bit of texture. A lot of this stuff you may just go up to Aaron or someone and say, I want the ABCD one or the HCP one. That's not a bad call. People have thought about them a good amount for those. So there's no shame in doing what they did. So I just want to touch again. I know that Tom touched upon this during his lectures, but I sort of wanted to return to this. We talked about those B values and how as you take a longer readout, you get more precision on the direction, but you get fuzzier and fuzzier signal, and you get less sort of a clear echo back. So a nice way of thinking about this is you're using these multiple shells, a nice clear image to increasingly more precise directional images as you go up, and you can actually align by using the multiple shells you can get a sort of a compromise of that good signal while still sort of being able to work out that path by overlaying those multiple shells upon each other. And one of the things, and this is his second lecture, he discussed, you've got your concern about orientation. If you have a singular orientation, then it's not so difficult, but as they start to path through each other and create more complex images, then you can see you get an increasing failure of those low B values that aren't able to really look down that directional path, and you get the increasing benefit and accuracy of the increased B values. So collecting more tensors along those where they have more directional input and lower signal to noise is not a bad idea. So going back to what we were talking about how you dispense across your shells. Any questions on that? Okay, cool. I didn't put in quiz questions this time because it's mostly sort of pragmatics, but some things to think about there is how you want to maximize your ability to measure the directional gradients with the higher B values to get more precision where that precision is available, and not necessarily in those lower B values. So sometimes you'll see people who map those B values out evenly across. It's doable, but you may not want to go that way. Okay, so top up, and I'm going to go through this relatively quickly because I think most of the time that you're using the multiband you can get the top up done, and the top up script, like a lot of the FSL scripts, are written for a Siemens scanner, and there's some translation that needs to be done to move more quickly onto the GE scans, and that's thankfully done without any direct influence. But one thing I want to discuss about the top up is that there's two different ways you can go about the top up. One way is when you, and I don't have a picture up about the distortions, but you know that if you collect, say, the anterior posterior, actually I've got a little picture down here, when you collect the anterior posterior or the posterior anterior, you get that skew on the brain. And you can your choice with doing the top up is if you're doing, say, a functional task or a resting state or something like that, then you want to collect at a high TR and map out those points in time. And you can't necessarily say, okay, do resting state for 5 minutes, and then come back and do resting state again, and then average those two images. Because what they're doing, for the first 10 seconds of a first scan and first 10 seconds of a second scan are really not the same functionally. They might be thinking, why am I having to keep on doing the resting state? Or, wow, this is really exciting. This is my first time doing a resting state and looking at a fixation cross. Life could not be this good all the time. Or whatever people think, I'm just assuming. So in those cases, you collect a mapping of the gradient one way, gradient the other way, and you build up that top up. When it comes to things like the diffusion, you're more able to just go, okay, if I scan your diffusion for 3 minutes and then in one direction, and I scan it in the other direction for 3 minutes, I can average. I can take those two, and probably not too much white fiber has moved in that time. You need to control for sort of the head shifts, but the actual underlying data should not have changed too much in those 3 minutes. If it has, you've got bigger problems. Your subject's brain is exploding or something like that. So pay attention to that instead. Okay, so if you're doing this, I'm going to talk today about how you're handling this, not for the bold situation, but for the diffusion, where you're actually combining that data. So we're going to create the top up, i.e. create the field correction on the B0 values for your various data sets. So the reason why I use a B0 is it's got a clearer definition, it's got your highest signal, it's got the best way of measuring how much distortion that's going on. So you're not doing it on the whole file, you're just plucking out those B0s, and they're usually the first thing you collect in the image, and you're creating your how much shift you need to do from those. The other thing you'll need to map it out is how much time you're collecting data, so your gradient time. So that's your spacing by your F vector, so how much time are you taking to cover that space. And you want to include two rows, one for your B0 of your, say, right to left, and one for your left to right, or from your anterior posterior and your posterior to anterior. I sort of skipped over that you can do inferior superior and superior inferior, mostly because you would only do that if you wouldn't do that if you've got axial collection, and most of the data you get in diffusion is going to be axial collection. It will be on a sagittal that you're getting that kind of information, and you're probably not going to do that. So up here is the basic command. This is my right to left, left to right merged B0 file, and here I have my my data in, which is my acquisition parameters. Here this is anterior posterior, this is this is right left, this is anterior posterior, this is inferior superior. So you would want to make sure you mark which one that is correctly. So in this case it wouldn't be for right to left. And this would be for this one marks an anterior posterior. And this config file is something that just comes with the system. This is sort of just general parameters, what blur levels you're doing, how many iterations you're doing, things like that. You can just use the defaults. There's no reason for you to sort of come up with your own ones, but if you want to, you can. It's available. And then you get out a field coefficient and your movement parameters of the adjustment. And so here, these are what you can carry forward to apply to your top up. So here you've created, based on those images, how much you're going to have to shift stuff around. And now this is the exciting bit where you actually shift stuff around. Um, so that first step is very similar between diffusion and um, between the diffusion and the epi, the bold. But here we have an example where now we put in the whole run of the left right. We put in a whole run of right left, whichever directions those are going across, and you pull in those maps that you've already created based off of this data, and you have the same acquisitions, and you're saying from that acquisition file. So right here you have it would be a 0, 1, 0 on the first row. Second row would be a 0, minus 1, 0, because it's going in the opposite direction. And those are indexed here, where this one is your first one, and this one is your second one. And then you get your top out data. So you've now got all your nice data shifted accordingly with those two directions now mapped into a singular direction. So what you often would do back in the days of single shell diffusion is you would collect the same direction multiple times, and you would just adjust the next NEX to amp that up to sort of get a more robust signal. Now if you're collecting two diffusion gradients, it's basically doing the same thing, where you're averaging them out, but also using that as a correction. So you get a nice, clean, relatively undistorted image out, and you can then you then have these tensor informations for each of those shells, and you build up each of those shells individually. So this one would have been done on one shell, and then you do it again for your next shell. So for your B values of 2000, and for your B values of 3000. So all your images are now nicely topped up. So that you may just get your data already with all the top-up corrections, so you don't have to worry about it. But that's a little bit about the guts and what's going on in that file. A lot of this information is then used in the eddy, so you may just create that information for the eddy. So that acquisition file that we were looking at before, where you have the first three saying what gradient directions you've been collecting, and you have you've got your acquisition file, you've got an index. We'll walk through each of these, but what you're doing essentially conceptually at this point is you're trying to take out those distortions, those eddy current distortions that Tom talked about. And the benefit of the FSL6 one is you're also getting a lot of other really nice features. One of the problems can be that if someone moves over the course of 3 minutes, 5 minutes that you're doing the diffusion, then that can both create signal distortion, and it can also mean that when their head is tilted one direction, if they tilt their head across, then the gradients that you believe you're collecting at are no longer true for that voxel, for that space, and that needs to be corrected. So, and also you may get those blank signals as you are collecting across time, and it gets interpolated out that your data is all misskewed and misaligned. You get those slice artifacts. The new eddy sort of is an all-in-one where it starts doing all of this cleaning and creating new files for you to do better interpolation. So this is an example of the command. You want to get a decent mask of what data you're looking at, and you can take in your input file, and this can be your input file. Say if you did it in dicom-to-nifty here, that will give you your bvex and bvals straight out of the file, which is really helpful if you don't have those directly available. if you've already done your top-up or field mapping, you probably already have those created if you're doing something on a standard package. You don't necessarily need to create these b-vals and b-vix every time. You can use the same set going into Eddy for everybody. You want to create a mask, and you can do that with FSL Maths has a mask thresholding program, or you can do it with 3D Auto Mask like we had done for the functionals. And what you can see here is an example of some of the slice artifacts that go in, and it's blinking back and forth between that wiped out gradient as someone passed across the gradient fields, and it's interpolating it based off of other adjacent directional files. So at this point, what you've got in the brick or what you've got in your Nifty file is a 4-dimensional matrix. The first 3 x, y, z, and that last dimension is not going to be time, but is going to be direction. And that direction is going to point directly to something in your bvex table. So as, let's say the first one's a b0, it's going to look different, as you saw earlier with Tom last week. And then after that, the next sub-brick, the next XYZ component is going to be a directional one, and you're just going to walk across those directions, and it's going to map onto your bvex. And you can use the adjacency of those bvex to better interpolate the data. So here you want to specify what encoding directions you've got going on in your data so that you can properly use that information. If it's already been handled in the top-up, you still want to inform it on how that was collected. And here we've got, you only need really 2 here for your rows in the acquisitions. You've got your b0 acquisition, and then you've got your tensor directions. You've got your acquisitions here. So that is what your acquisition parameters are for your b0, and then all of your tensor directions will follow similar acquisition parameters. Yeah?
And you said that the adjacency helps.
Yeah.
Just like how close.
Another directional tensor is. So it's a way we used to do it is we used to do things like average the adjacent slices into that space, but that's sort of somewhat imperfect because you're just assuming that that whole block of area is showing a similar direction. What's nice is being able to interpolate other directions that you could then build up what the direction was on that one that you lost during acquisition. So when you're sort of going through each of those scans, you're sort of peeking down a direction this way, down a direction this way, and you're randomly going, not randomly, in a pseudo-random order, going across directions, so you're not constant. So you can imagine if someone went through a coughing spell, that they would knock out a lot of adjacent directions. So if those are all collected in sequence, you would be blind to one direction in space, of one white fiber direction. But since you're sort of sampling somewhat at random, and then you can interpolate back to the one that you missed based on if you had 3 spots surrounding it that are all showing a strong signal, you can expect that the one that you're missing would also show a similar strong signal. So you can interpolate it that way, rather than just going slice above, slice below. Cool. So, the bvals and bvex will come out of DICOM to Nifty, but as you feed them into Eddy, what you're going to be looking at is just a 1 row by all your acquisitions for your b values. 0 for your first one, and if you have multiple v values, it can be scattered throughout there, and those will be averaged. Those can be averaged into creating that image, and then all of your b values mapped accordingly. And in your BVEX, your you'll have 3 rows by the number of acquisitions. So you might have to again rotate the information out of DICOM to NIFTY, but you will map out what that tensor direction is. So those will be in sort of a value from 1 to -1 in the sort of X, Y, and Z direction. And the top, you know, I guess the furthest in the right and 0, 0 on the left would be right here, and that'd be a 1, 0, 0. And you could sort of map across. And you may have, you'll probably be running eddy on one shell at a time, but keep in mind, with multi-shell sequence, you would run in your B-vals and BVEX one shell at a time as you get your correction in eddy. And you get, after all of this, you've now done your eddy correction, you've cleaned out your junky data, your slicey data. It looks a lot nicer, and you're dealing with a rotational vector set that matches what your data was collected at. Does that make sense? Any questions? Insights? Okay. So the top-up and eddy correction is you want to do no matter how you're going about your diffusion. From here on out, what the next step is working out what that diffusion data set actually means as far as fibers. And we're going to talk about 3 basic approaches to understanding that. I'm going to skip a little bit over just the basic measurement of FA in DTI fit. That one, and I think you're hitting a little bit of DTI fit on the Friday. It's very easy to use. You throw in these diffusion, you throw in your diffusion nifty file, and you get a measurement of what kind of a sphere fits over, how elongated it is, what your eigenvectors are, and Tom spoke about that a little bit last time, where your strongest eigenvalue and going across, and you get your mean diffusion, and you get all these nice little metrics out. But this method has the weakness of not handling crossing fibers well, because each of those little voxels with its eigenvectors and all of that doesn't take into account that if you have 2 crossing fibers going across each other, that it would also create an inflated sphere. So the way that for the basic DTI fit, you don't get into that too much, but it's a nice quick evaluation of sort of your overall FA values. So what is TBSS? This is track-based spatial statistics. So the idea of this is that instead of just sort of marking out that the branes are about in the same location, that you're in NMI space, like you do with the functionals, you're actually not going by the outside of a brain, you're going by the internal skeleton of a brain. So by working out the FA values, you can sort of see where you've got white fiber. So, you know, that's why you can sort of think of it as a skeletal. You're seeing what the white matter, the bone of the brain, I don't know. No one actually calls it that, don't quote me on that, but it's sort of the skeleton underneath it. And what you're doing is you're then aligning them morphologically. And TBSS is being built up into a package that just nicely, calmly walks you through that. So once you've got all of your data through Eddy and you've got your directionals and you do your DTI fit to get your FAs, you can put all of your FAs into one big directory. And then you can run the first step in the processing, where it looks to move all the brains into the correct space, make sure that everything looks right, and you can look at how that turned out by in Firefox just opening up slices. This is a good first step. If you've done everything along the FSL path, this should turn out just fine. If you've sort of switched back and forth between different processing paths, maybe a little bit in AFNI, maybe a little bit in SPM, or what have you, then sometimes you'll notice that the right to left, inferior, superior has all been switched around, and the brains will come out in a very weird basic alignments, and you would want to check it here. Next is that nonlinear registration that we were talking about. So once it's sort of put the brains in about the right spot, it'll go through and it will build up it will work out where all those brains are, work out a template for everybody, then you can apply everybody's morphing to that template, and then you can create a mean skeleton from those. And this last step is just thresholding it so that you've got what's in brain, what's out. It's kind of like the auto masking, but you're just thresholding what you're considering as a fiber. Once you've gone all the way on getting all this track-based statistic data, you can put these into randomize. I'm not going to go into randomize here, but it's this would be done just like with anatomical VBM in FSL, or like any functional in FSL, that you can do permutations testing to see if your group difference is substantial along parts of this fiber. So this isn't the same as just looking at voxel heat maps, but it's in the same genre, that you've got FA values all across these white fiber areas, and you're looking to see if any of particular areas along this skeleton differ between groups. So this is where I want to go back to that question of crossing fibers. If you have crossing fibers, you're going to have you're going to have a very low FA value. It's not going to be, it's not going to have one eigenvalue that's much larger than the other ones, and it's not going to show such a path. And it's going to have the problem as well when you're working with the FA values, that you may be looking at, basically, I think about it as the quality of a road. So when you look in Google Maps and you see that there's all these roads everywhere, and you go, oh, there's lots of roads here, we've got lots of roads, we're good. There's not so many roads here, that's not so good. But if you have lots of potholes, if you have like sinkholes where large sections are gone, then those fibers going out aren't going to do you as much good. If you don't have a path connecting all the white fiber, that's going to be more of a concern about the person's brain. And when you're looking at things where people have had strokes, or if they've had a TBI where you've got breaking of the white fiber and you've got sort of dead zones above it, just looking at which roads are intact isn't going to tell you too much if you can't actually drive all the way down those roads. So that's where you get more into some of the concepts of tractography. So in this, you're looking to see if you can actually path. You're looking to work out a vector, a path in each of those voxels, and you can actually map those, what are possible arrangements that can give you alignments. So the bedpost method is also called the ball and stick model. So the difference being between the general diffusion model, where you just have a general sense of how skewed and the direction of skew of any given voxel, you build up a vector, and it can have multiple vectors through. And these optional vectors, there's an uncertainty to it. So there's a number of different fits that could work, and by lining these all up together with the uncertainty of where they might be going, their probable direction, you can then start pathing down all different probable tracks until you have a setup of roads that make sense. So it's sort of going back to our Google Maps analogy. You might not have a resolution to see what's going on at intersections on Google Maps. You might have a couple freeways bumping into each other, and you can't really see where all the individual paths are. But there's a probability of different ways that could actually work, that could actually connect those things. And as you sort of build up a map of the potential possible arrangements that could lead into those roads, then you can start building paths out. So, running bedpost, this one it's one where as long as you have your correct input data and effectively labeled, so you have some clean diffusion data, and you can call it data nifty, and you have a mask, and your bvals and bvex, you can run that subdirectory through bedpost, and it will go through and it will recreate a mapping of how all these directional gradients can go in light of this sort of probabilistic tracking. This, what kind of vector could path through to build up this arrangement. And this has the obvious benefits of now things that before looked like holes in your FA or decreased areas of FA can now make more sense as path through areas. Does that make sense as sort of conceptually what we're doing here? Cool. And feel free to stop me at any point if I'm not making sense, or if you come up with a better analogy for anything, or or if you just want me to stop talking for a while. I take no offense. So, prob tracks is the next step of, okay, what do you do with that? Now that you've got this sort of idea of a roadmap of a brain about where all the white matter's going, you can build up networks, you can build up targets, and you can create seeded and masked data sets that you can work out how connected various spots are. So you can put in a whole brain mask, and you could be mapping between all these different locations, and you can work out what is the strength of it, how many paths do you have connecting through, and which ones are connecting to each other. So one of the key outputs you get by default is your way total. So what this means is it's a text file containing, for your masked regions, what's the total amount of pass-throughs as a waypoint. How many times are you getting data going through that area, the number of tracks that are pathing. And you also get a density map out from that you can use for future analysis, and depending on what you request, you can get various connectivity matrices. It'll depend upon what networks you feed in, what target maps you feed in, and what matrices you ask out. So that is the resultant you get out of doing the prop tracks approach. So just to create a counterpoint, I basically talked about FSL this whole time, but that's not the only game in town. Um, a few notable packages um, are Noddy, um, MR Tricks, and DSI Studio. I'm going to focus on DSI Studio because I enjoy it. It's fun. Um, if you guys want to play with it, it's a bit of a beast to install, but once you've got it installed, it's actually quite nice to work with. Again, for starting to work with it, I would take everything through the top up and the eddy so you have the cleanest data possible. But at that point, it's going to create a different way of calculating out what the likely fibers are in the fiber crossings. So we talked about the general DTI model. We talked about the bedpost model, where you're mapping out potential paths through, and the DSI approach is very similar. So you that you start building up potential explanations of how that data is mappable. So you create a Q space. Now, um, Q space is at least descriptively like a K-space for diffusion. So instead of having your phase and frequency encoding, you have a gradient encoding, and it's how much delay in that phase it is. And from that, you can start building up a way in which that space can be covered. And a lot of these terms here are almost unworkable, like ensemble average propagator. Why they called it this, I really don't know enough about sort of the maths behind to elegantly say. But what it is it's a probability of displacement. So it's a probability in which you have a diffusion along that space. And again, here, when you're talking about ways of mapping those roads in that weird crossover areas, and that's really the focus of what we're talking about, is those crossover areas. You have probabilities. What are the options that you have for a tractable path? Another term you'll hear a lot is hardy, which is sort of a description, which is sort of the high angular resolution imaging that you can get to try and pick up those crossing fiber paths. So once you get that, you can then try to map out what is the most logical diffusion gradients that would create this model based off of the adjacency of the available data. And there's various different ones that it offers, including GQI and ODF, that are just basically fit algorithms. So if you model that connective path different ways, you get different fits. This you can also summate to be something representative of that FA. So representative both of the path, but really what we're looking for here is to create some tracts. You can do this on the command line, or you can do this on the GUI. I'd suggest if you're playing around with it, go through the first one on the GUI, just so you can see what's going on, and you can, modify any parameters, see any big gross errors. But if everything is going great, then you can move to doing it on the command line, which is a good deal more elegant. So here's an example of a BVEC table where they have multiple B values coming in, and they have the vector file in XYZ. And it automatically finds things that look like bad slices. Hopefully, if you've run this through eddy, you've found a lot of those bad slices, interpolated them, and worked with them. But if they need to be deleted out, then they can be done so at this phase. But we can then create a from that we can create some estimates. We can create the um, source file that's needed to work out those fiber tracks. This is a combo move where we both do image registration, masking, and we also can specify some of the basic features that we want just sort of basic DTI, or we want to use the ODF. We want to use those fiber tracking paths to get something we can use nicely in tractography. This one sort of nice point is this can do morphometrics. It can do it to your anatomical, and instead of using the FA maps like you do with TBSS, you are using your spin distribution function. So you're using actual mappings of those paths and morphing those into place. So you get a nice clean fit by doing it this way. And the two ways that you can use this data, once you have all these tracks pointing everywhere, is kind of like the same that you were doing in ProbTracks, is you can point it to a mask and it will create a network statistic. So it will, when you talked about resting state, one of the things you would talk about is those graph metrics. So the two areas that graph metrics are particularly relevant is in resting state and in diffusion. In diffusion here, we're talking about not how correlated two different bits of the brain are, but really the strength of the connection. How many fiber tracts are connecting two places? What's the strength in those fiber tracts? And built off of that, you can get those same graph metrics out. How interconnected, how many connections, strong connections, either binary or weighted, does it have to all the other regions that you've picked out? And just with a very simple command, you can get all these wonderful graph metrics out and more in the newer versions. You can also do regression and general ANOVAs nicely in the GUI interface. So here's an example where we read in a table, we did a correlation with age, and we did a whole bunch of permutations, so we can see how is our actual analysis performing versus the permutation set. And this is something that we talked about earlier in the benefits of randomize and the problems with cluster gate, and really with the computing power available now, permutations is where you want to be. This does a nice job of giving you some nice text that you can throw into a paper. It doesn't do interpretation, but it does methods. And it can give you the significant paths, looking across all the paths of the brain, what ones are actually significant, once testing for permutations and your multiple comparisons. And it gives you a very cute, nice GUI interface for then mapping out these tracts, and you can get the extraction values from those. So this is both of these. This will give you something very similar to what you can get with Bedpost and ProbTracks, but some of the aspects of how it does the registration and how it maps out those crossing fibers will be different. Some of the interpretations of the features will be different, and there's strengths and problems with both of them that you can point to defend whichever one you decide to go with. Sorry, just being coy. Okay, so with that, those are the main methods that I wanted to sort of discuss and sort of give a context of both how you go about using them and what they're looking to solve and how they're looking to solve it. But that's basically in record time everything I wanted to hit today. But I want to check, does anybody have any questions, anything that they'd like to know more about, or um, anything of that sort? Okay. Yeah?
I have a few questions about how to interpret weight totals and differences in FA.
Mm-hmm.
So with weight totals, if you have less streamlines, then you can say biologically there's less axons.
Right.
But if you have a decrease in FA, how do you interpret that? Is that just saying that there's the integrity of the myelin is decreased, or
Yeah, I mean that's sort of one of the sort of issues with the FA values is that the FA value tells you sort of how stretched you are at that particular vector, that particular location. So loosely, you're just talking about when you map a whole bunch of people over each other, they probably have similar crossing fibers at similar places, and you're making the assumption that your loss of signal at a location of crossing fiber isn't going to differ between groups too much. And yeah, that if you are in an area where one group has a nice clear fiber bundle pointing in a clear direction, another group doesn't, that's because of demyelinization. That's because there's not a constraining force at that location. But the those streamlines and those that the bedpost with its waypoint analysis, you actually are pathing those through and seeing, okay, what's appears to be the the strength of that path going through, and you're comparing it that way. So essentially, they should indicate, if you've got a clear problem that's detectable on the FA, you should still find that on the bedpost with your waypoint analysis, your weight total. But you're not, you wouldn't necessarily expect it vice versa. That if there's an area where those crossing fibers will give you a muckier answer, and or that you have a break at some point along a fiber bundle, and it's just that's going to be picked up with a tractography in a way that's going to implicate that two brain regions that may be distal, if they have an area that's knocked out, that's going to affect communication between those if there's no direct connecting fibers. Any other thoughts, questions? Well, okay, then feel free, if you come up with something, especially if it's a really hard one, ask Aaron on Friday. Yeah, I had to rush that one because he was heading for the door. Okay, but yes, you can always